I also take this opportunity to welcome our school children in and out surroundings Roorkee, and also thankful to the teachers and the principal, all the schools who have really take it very seriously and send the students this morning to have this make this event very successful. And I really thankful to the teacher that he joined us in this morning. It's really very chilly in the outside for kids. So let me tell you the little bit of this program. This is very briefly for the students. Today we have our science outreach program to young students. They have been focused, if you look at in many research activities, government of India and outside and abroad also, that it is a very integral part of any conference, that at the same time as we are looking for science and development, and it is also an opportunity for young students to get motivated and listen to our eminent speaker. So as a social kind of responsibilities, the CFOS 2020 organizing committee also thought of that we'll be having this responsibility and we'll spread this science program to have a part of our different school students. And as you know that so this morning we have a very popular science lecture and then title Let's Talk Chemistry and Outreach Event. And we have Professor B.C. Ranu. He's a wonderful teacher and he don't need any introduction because he's very popular chemist as well as is very popular to the young children and us also. He's our teacher, so he has a vast experience for such kind of research program and activity. And we are really thankful, sir, that you have accepted our invitation to be here this morning, because very recently he came back from Russia and he just, I don't think that he is immediately came join us for this program, and very thankful to sir for your and accepted our invitation to have you here for because of only the student children. So before we start with that, I'd like to just introduce maybe the few schools who have really accepted our invitation and extends our greetings that they will send our students, their students here this morning. So we have Adarsh Bal Niketan School, IT campus, Montfort School, Mount Litera G School, Army Public School number 1, Army Public School number 2, Kendriya Vidyalaya number 2, SP Global School Roorkee, St. Anne's Secondary School, and Delhi Public School. So with this, I welcome you all and the teachers accompanying the students, and I wish that you will be having a wonderful time 1.5 hours here. So with this introduction, I kindly request Professor B.C. Ranu to have this floor. Sir, this is up to you, sir. Yeah, thank you.
Very good morning, everybody, particularly my young friends. How are you? Good, okay. And I thank the organizer, Debashish and Anuj, for inviting me and giving this opportunity to talk to you, to share some of my thoughts about the chemistry today and future. So, first thing that about chemistry, I mean, all of you love chemistry, I love chemistry, fine. But your neighbors or the common people, what they think about chemistry? If you ask your neighbor, any of neighbor, what do you know by chemistry? Immediately the chemistry, oh, chemicals, oh, they are so bad. You ask the second person, what they will say? Chemicals, no, that's all polluting, oh, obnoxious, right? You the third one, what you will say? Oh, chemicals, they're all bad. They're destroying my skin and so everything. But actually, is that the chemistry, that is the real picture of chemistry? No, this hurt us, this hurt you. But if you look at the same people, when they're sick, what they're taking? They're taking some drugs. What is that drug? That's a chemical. So the chemical saves his or her life. They forget. What they're using in a mobile or in gadgets, they're all useful materials, they're all chemicals, polymeric or whatever. So that increases the comfort of our life, right? These chemicals, the fertilizers and all the things that increases the production of crops. All these are good things that are good, say about 90% good, but 10% bad. The people remember only the bad thing about you. That's the same thing for you. You've done so many good things about your friend, but he or she will remember only the bad things you did. That's the nature, okay? So how to remove that? How to eliminate this bad name of chemistry? That's what I want to talk about. Okay, you also want that, right? Okay, so how to do that? And that's what I tell that if we follow nature, if we follow the green philosophy, then really we can eliminate the bad name or drawbacks of chemistry. That I will come at the end, how it's possible. Okay, so so the title my green philosophy in chemistry. What is green philosophy? Green is very common term, and green is good, and you see the green everywhere. And if you have greenery in your house, you like it. So what is green philosophy? It's nature's philosophy. What is nature's philosophy? This reaction. All of you know about this reaction, but that's my most favorite reaction. That is photosynthesis. You have studied in class 6 or 7, okay? And what is that? Have you thought of this reaction? What is this reaction? This is the reaction of carbon dioxide and water to produce glucose and oxygen. Very simple reaction. But I will analyze this reaction. I will spend some time on this reaction. That is the key point of my talk today. So, carbon dioxide is abundant, naturally abundant, cheap. Water abundant. And what I'm making is that glucose, very useful substance, and oxygen. I should not tell what is the importance of oxygen. Actually, if this reaction is not practiced by plants every moment, we could not survive today. That's where you will get that oxygen, okay? So that is the most important thing. Now you analyze it. The plants are using, okay. Plants are using carbon dioxide, which is non-toxic, environment-friendly, abundant, renewable. Water, the same thing, and we're making these things. So here, if you look at this, none of these chemicals which are produced are bad. None of these chemicals which are using is bad. So this is non-toxic. Starting the reaction with non-toxic, environment-friendly material, producing the material which are environmentally useful. That's the first thing, nature's philosophy, nature's rule. Okay. Look at this point. Any reaction if you look at your textbook or whatever you have knowledge, that just mixing two things does not give you the reaction. Just you need some reagent, some condition to get the reaction. Okay. So here, what they use chlorophyll, that's the catalyst. That's the inherent natural catalyst. And sunlight, that's the nature's energy. No organic solvent, no solvent here. Organic solvents are very bad. Almost all the organic solvents have some bad or more or less some bad effects. So, but if you look at a textbook or any reaction, often you are using organic solvents. So these organic solvents are problematic. They create waste. They are harmful effect, like carbon tetrachloride, benzene, they are really, really very bad. Okay? So, but plants what are doing, they are not using an organic solvent. They are not using any other bad catalyst. So they use chlorophyll. So that's the thing. So once again, I'm repeating it. Next I will come. What's the nature's philosophy, nature's theory, nature's learning is that use chemicals which are environment friendly, produce chemicals which are not harmful. First thing. Use the reagents and catalysts which are also not toxic, hazardous, anything. That's okay. And use the energy as much as possible from nature. Okay, that's okay. Now let us summarize in the next slide. So what do we learn here? That use of reactants that are non-hazardous and easily available, generation of products which are non-toxic and useful, use of solvents that are environment friendly or no solvent, I will come to that, use of catalysts that are non-toxic and inexpensive, and use of sunlight and reaction at room temperature as far as possible. Whenever possible, design your reaction so that you can do it in sunlight at room temperature. Okay, so I will elaborate. Okay, and here you can note down this DOI number so that you can get that access of this paper. Recently, I wrote an article in Chemistry Teacher International, which is meant for the teachers and the students. Yeah, what is that? Learning green chemistry and its principles from nature's process and development of green procedures mimicking nature. And that's what the topic of my today. So I will concentrate mainly on this paper, which I talked, that's okay. And you can, that's it, I mean, it is a widely appreciated paper. After writing that, I got many mails from anyone. So you can get this, download this paper and can read it. I hope you will like it. The teachers and the students both, okay. So that's thing. Now the question is, this we learned from the nature. Can we practice it? Now the question is, can we do chemistry in our lab, in our day-to-day activity with this learning? Yes, it's possible. Okay. Let us now the real life. What is reaction? From your knowledge, that's when you do anything in the lab, you mix two things and get something new. Okay. That's the universal thing, a general thing of any reaction. You are mixing A plus B. Okay. You are mixing A plus B in presence of some catalyst, solvent, and energy means heat or thing, you can get C plus D, usually. Okay. But what happens is this, when the industry people are doing reactions, when they want C, they don't care about D. They just dump it anywhere. There lies the problem. The D may not be good. If they're toxic, they are creating pollution. Okay? So that's the problem, that the chemical which they do not want, they dump it anywhere and creating problem. Firstly again, this A plus B, which are reactants we call it, these are also not always user friendly, environment friendly. You may not know, but you may recall that Bhopal's accident, that is use of methyl isocyanate, that was one of the reacting partner, reactants. So that leaked and killed so many lives. So that was the thing, the green path or nature's path was not followed. So you cannot use any chemical which are toxic, hazardous, or not environment friendly. That's the thing, okay? So how the catalyst should also be there. I put it in red part because catalysts are not always very good. It was. And the solvent, organic solvents I already told, and the energy, if possible, usually if you look at the reaction, always hit it, 100, 150, 200, whatever. So that much energy we are using is coming from fossil fuel. All electricity that's coming from fossil fuel. So whether we can avoid it. Okay. So what should be the ideal thing? Ideal thing will be that we will do the same reaction, but using green catalyst, green solvent, and green energy, which we call green tool, all three. Green energy means sunlight, that is the ideal thing. But one thing, and make C or D. Don't produce any waste. Don't produce any side product which can cause harm. So that should be the real objective of any chemist today. Okay? Either you can, and that's possible. I will show that is possible. So either C or D. so that you are eliminating the production of waste or production of byproduct. Okay. So you can design your reaction in a way that you can achieve this goal. I'm not talking about the ideal thing. I will show the representative example of each thing. That's one or two examples that where this type of chemistry can be practiced. And also I will show at the end that even in this symposium last 3 days, the active scientists which are here, there are many of the reactions they are doing in following this path. Okay. So now people are concerned, industries are concerned about the production or generation of the waste and toxic chemicals. So world is changing. Okay. So I will show that for in your thing that you can understand that really it's possible to do the chemistry. Okay. Okay, so that's the thing that how we can implement by using nature's tools. Again, I'm telling by using nature's tool, following the nature's path. But one caution that it's not always possible to follow 100% the nature's way because nature is almighty. I mean, nature can do so many things. They are producing millions and millions of compounds by following the same path, but we cannot do the things in one day. But whatever we can, our objective, the objective of the chemist should be to follow the nature as much as possible, and one day we can make this world a clean world. That's the thing, and that's the I want to tell you or convince you through my lectures, through my examples, that is possible. That is, I'm not talking utopian. Okay. So give some examples. That okay. As I told you, what nature is doing, using water, using nature's catalyst. Okay. Very simple thing. Reduction. You always know what is reduction. And a simple reaction, you know already, you have on your 11 or 12 class, that reduction, and the reduction of simple ketone to alcohol. You know, you use sodium borohydride, lithium aluminum hydride, all the things. And these things have some bad effect, okay? But here is possible. That's one representative example that you can do the reduction using some nature's thing. That's carrot, you know. All of you know the carrot has antioxidant property. And that's why we use, doctors say that you take carrot and all the things that can, look you younger and all the things because they're antioxidant property, okay? Use the same thing in chemistry. That means antioxidant means was reducing property. So if you use fresh carrot, that's you can finally chop it and all the things and you can do it water, you can do the reduction. There's enhanced selective reduction. So it's possible. If you want to design, if you have a mind, you can use nature's process. You can mimic nature. Okay? Yes. Okay. Now whatever, if you have something, some question or query, just note it down. After my lecture, I have 15-20 minutes time to interact with you. So please keep in mind or note down. I will try to answer all of your queries. Okay, as much as I can. Okay. Okay. Another reaction again. Like chlorofluorothiazide, that's a very difficult reaction. The conversion of glucose. D-glucose is a non-aromatic thing. It's not an aromatic thing. You are converting a non-aromatic to aromatic alcohol, catechol. It's not very easy to do in lab. Whatever reagent you can in synthetic lab we have, in one step, impossible. Even if you use some steps, it's very, very difficult task. But what you see it here, if you look at the E. coli and water, room temperature, you can convert that to D-glucose to catechol. You know aromatic compound. What I want to say you may not understand everything, but the salient feature is that you are converting a non-aromatic compound to an aromatic compound by simple way using E. coli in water. That's fantastic. Okay. And here, one industrial example. Again, I'm telling that I'm not telling something, unrealistic. Here, the industry, many industries now are using this biotechnology or these microbes and enzymes for the reaction and making money. Here, one is the D-glucose, you know, the nature's thing. Again, you can get it natural product. So from D-glucose, they're using the E. coli and all these microbes and they convert it into vanillin. And this is a commercial process. I'm telling they're making tons and tons of things. That's vanillin. You know how useful is vanillin. We use it vanilla, what you call vanilla. That is vanillin. We use it for our food supplement, for even say flavor and all the things. So vanilla is a huge market. So, and the same thing on D-glucose in another process, they make it vitamin C, you know, how important is vitamin C. So these things, if you look at the company, this company making, so using this process, how much money they can make. So these are the industrial process. And if you follow the nature's process or the green path, the industry can be profitable. Now, many industries in the world, even in India, they are just redesigning their process, they're converting they are not using their old process, they are now making the new process, green path, where they can make the molecule following this, okay. So that's on the industrial, there are many examples, but I give the industrial example that type of chemistry can be practiced in industry, okay. Okay, that's one real life example. It's from my lab, but that you can make the reduction as simple following the things. Again, I'm telling, if you cannot do it 100%, do it how much you can get. This is nitrotiamine. You know how to reduce nitrotiamine? Can you say one minute? Usually, what you do with NaCl or any other reducing agent, that is not very good. Okay, so how can you do it? But in a simpler way. That's one of the things. And okay, what I'm telling here, okay, using some iron nanoparticle. You know, iron is very cheap, nature's thing. And how to make this? You have take some sodium borohydride. That's relatively, less toxic. Okay, so here is sodium borohydride, or you can use tea extract. I'm telling them, no, don't use sodium borohydride. You can tea extract. We did it in my lab, no problem. We published the paper. So use tea extract, and here is the more salt. That's also a very non-toxic thing. And put that tea extract here. Immediate, that can be demonstrated in lab. Okay. So what do it, then immediately you find that a black solution, and that's iron nanoparticle. Okay, you know nanoparticles. So we made it in the lab. And what is the importance of this thing is that you can separate this nanoparticle with a magnet. You can some bar magnet, you can get all the nanoparticles there. So that we made nanoparticles. So just with tea extract or any reducing agent, and then more salt, you can get nanoparticle. Now, very nice reaction. Here you have any nitro compound, any nitro, and put it there in that solution, water than this, room temperature reaction. I mean, again, I'm telling it that not other any other energy or C, that normal temperature here, you can get. I mean, after some time, you get that black color is giving orange color. And whenever you get that, we saw the TLC, the reaction is over. So that's a very nice reaction. You can get this, then you can get all amine. Okay. So what again, without using a toxic reagent in water at room temperature, you can do the reduction of nitrotiamino. And amino is a very important group. You know, all the heterocyclic compounds, and we have the amino acids and all the things. Amino is a very important group. So conversion of nitro to amino is an important fundamental process. Okay, that you can do with this. Okay. We have many examples, don't worry about that, but what we showed it here, that you have in presence of other functional group, you know, there is the olefin. You know, olefin gets reduced very easily. So if you have olefin and nitro, only nitro is reduced, no olefin. Similarly, acetylene and other groups. Okay, so this is a very effective method of selective reduction of nitrotiamine. That I want to say. Okay, there are other examples, other say CHO and all the things. Okay, don't worry about that. But you can process is that iron nanoparticle, water, room temperature. Okay. Okay. And it's not my work, but I like it. Okay. Here to look at this very important reaction. Again, following the nature's path, that no use of any organic solvent or any other all the things. Here, look at the thing. That's It's a 4-component area. 4-component means 4 chemicals are mixed together. Nothing. You just make, there is a hydrogen, and that's an beta keto ester. Okay. That's an aldehyde, hydroxyaldehyde, and malononitrile, or simple chemicals, cheap chemicals, water, no catalyst, nothing else, at room temperature, just mixing 5 to 10 minutes. And you are getting this material. This material, this is, say, benzene ring, and you can say pyran or so, and that's a pyrazole. So all these things are heterocyclic compounds, and they are important constituent of many drug molecules. Okay, so these compounds are itself is very important. But look at the chemistry of it. We are not making any, all condensed together and we are getting this, we are not making any waste. We are not producing any waste or bad chemical. We are not using any organic solvent. We are not using any heat. That's the nature of learning. That you can practice this chemistry in lab, make this important material. Okay? So that's one thing. They have made so many materials that are in high yield and all the things. So again, that's another example of doing the reaction in water at room. There are many. If you look at the literature, there are so many examples of this type of reaction. Just I want to show you that some representative examples that type of chemistry can be practiced in the lab. Okay. Another important thing, similar reaction, that is pyranopyrazole. Okay, I'm explaining it. This molecule, this is pyrano molecule, as already imported, and this is pyrazoles. Okay, these molecules also can be made by 4-component reaction again, similar reaction, malononitrile, aldehyde, hydrogen hydrate, and diethylnacetylene carboxylate. And here, you look at this in the water, in this little heat, 55 to 60, you can get this molecule. So that's also another very important reaction. Following this path, you can make these things. So this is possible. And no, again, if you look at the things, no side product or nothing. All are absorbed here. The atomic economy is very high. So you can make these things. Okay. Similar thing again. That's again from my lab. Okay. Here we are making dithiocarbamate. I'm using it. Dithiocarbamates are very important material as agrochemical. What is dithio? Sulfur is thio. So there's dithio, N is here, so dithiocarbamate. There are many methods of making dithiocarbamates. They are so important compounds. They are used as agrochemicals. They have used some also in the pharmaceutical compound. So here we have used diazonium fluoroborate. That's carbon disulfide and an amine. You can get this. This I talk the diazonium fluoroborate, not very good thing. It has some toxic effect, but it is relatively less toxic than other diazonium salt. It's a solid. You can make it very easily from amine. And after the reaction, what happens? This is all condensed. Nitrogen is evolved. That's not, toxic chemical. Fluoroborate is, it comes out of fluoroboric acid. You can recover it. So that's not going to the drain. You can recover it. So in that way, that you can see in water, room temperature, you can make this dithiocarbamate without using any organic solvent and all the things. And these compounds are solid compounds. You can recrystallize it from ethanol. So whole process does not use any organic solvent. And whatever I described earlier also, they don't use any organic solvent in the whole process. So that's the thing, that you are avoiding use of organic solvent. That's a great thing. Say, whenever you are doing practical in the school lab or college lab, myself also at our time, we use benzene, carbon tetrachloride without knowing anything. That's really something we are, harming our health and this. That should be completely destroyed. And in the lab also, the use of organic solvents should be minimized. Okay. Okay. We have many examples. Don't forget about that. I'm not coming to the details of this. Okay. Okay. What I'm emphasizing here, this is transition metal catalyst free. That's again one of the green path. Reaction at room temperature, that's energy efficient. Water used as solvent, and synthesis of variety of aryl dithiocarbamates. And that's important. The isolation of products by crystallization of crude from ethanol with high purity and yield. So industry loves it. Industry, they don't want chromatography or anything. They want, if they can isolate the compound by simple crystallization, that is good for them. Okay? And whatever you're doing in the lab, academic things, that is not pollution. Pollution is that industry. So industry, they are using tons and tons of material. So the center of pollution is the industry when they are using the bad chemicals or when they are producing the bad chemicals. Okay, another reaction that, Michael reaction. I think you have heard of Michael reaction. That is, or if you know, I will let you know, that's okay. Michael reaction is a very good reaction, lots of applications. And this is Aza-Michael reaction, where you use the Aza means nitrogen. Some nitrogenous compound, when you do the Michael reaction, you can get this product. That's a very important reaction, that's why I'm showing it. And that can be done also in water, room temperature, and that's 20 things. So these are the simple fundamental reaction. You can do it in water without using the organic solvent and energy. That's what I want to carry forward. Okay. Okay, and we have made many molecules here, but I'm not going to the details of it. Okay, okay, mechanism is water. Okay, I'm just skipping it. Yeah. Now think solvent-free reactions. As I told you, all water using, but can you do it without solvent? No water, nothing, no solvent. That's also okay. Solvent is really, really bad. Okay, but is it possible? I will give one or two examples here. Yeah, that's again from my lab. Okay, here, this is dihydropyrimidine, very important molecule. Dihydropyrimidine molecules have lots of pharmaceutical importance. Still now, the derivative of this unit was used as a medicine for AIDS. It has anti-cancer property. So this molecule has many views, and if you look at the Google or any book, there's maybe thousands of hits of making dihydropyrimidine. Okay, that's many things. And one of my paper that's contained the dihydropyrimidine, I think now is 700 citations. 700 citations, one original paper. So you can see that this molecule, dihydropyrimidines, is a very important molecule. Okay, there are so many methods. The original method using sulfuric acid and all the things. But again, look at the things. Thus you mix three things. That is beta diketone aldehyde and urea or thiourea. You have to heat it. Heat it in 1 hour, you can get this solid compound. Now again, you have to heat. If you can avoid the heat, that is the ideal. But as I told you, if you can have the 100%, okay, go, whatever. You avoided organic solvent, you have avoided other things, and no side product, nothing, you can get these compounds. So this is another important compound, and yields are very good in all the things. So, and we can make it in, say, kg scale. It's possible. We can make it in kg scale. So that can be a good method for industry also. Okay. Okay. I will come another thing. Introduce the new thing. In our symposium also many workers are using that mechanochemistry. This is called, I'm introducing the mechanochemistry. Okay. All of you know that this you can, all you identify. What is that? Mortar pestle. You use it for so many things at home and this. But chemistry started with this mortar pestle chemistry. So when chemistry started, they used two things and then pestle it in a mortar and got new compound. That's the origin of chemistry. But then even in our practicals, I don't know whether it is practiced now in the colleges, when you have a carboxylic acid, we made carboxylic acid to acid chloride. On the mortar pestle, solid carboxylic acid, then phosphorus pentachloride, and then pestle it, and we can get acid chloride. So I don't know whether it's practiced now, but that's also this chemistry. Now this chemistry came in a sophisticated way, that ball milling. If you look at this, that's the same thing, the ball milling. And this ball milling is a pulverizing machine consisting of a rotating drum which contains pebbles and metal balls as the grinding implements. It has some balls, and you put your reactants there, turn the switch on. These balls are rotating in a high speed, giving the mechanical energy to the things, and your reaction is done. So you are applying mechanical force to the reactants to form a new compound. And this branch of chemistry called now mechanochemistry. That's a new branch of chemistry. But actually, again, if you look at the thing genesis, it's following the nature's path. It's following the green path. That you are applying mechanical energy to reactants to get a new compound. Mechanochemistry is now very well talked about things. Now, chemists are using it regularly in their lab, this mechanochemical reaction. And you can generate new chemistry. I will show one or two examples of these things because they are again mechanochemical reactions. They are done in a green way. Okay. Here's one for dihydropyridine. You can see that this is pyridine. This is dihydropyridine. They are also very important thing pharmaceutically. You can make it thus, again, 4-component reaction, aldehyde, that is acetylene dicarboxylate, and then amine, aniline, and then this dimalonitrile or so. Then you can get no solvent, no catalyst, just grinding. No solvent, no catalyst, grinding. Look at again the photosynthesis, right? The same path. No catalyst, no things grinding, you can get this molecule without any side product. So that's the chemistry. You can get so many molecules, you can make it, and then you can get all these chemistries things. Okay, and here I'm telling you another thing. You see whatever written here in the bottom of all slides, that means this work has been published in this journal by these people in this year, in this volume. Okay, and this page number, this is page number. So if anybody interested, he can look at the journals and find out the original paper. Okay, so this is the usual way of writing the reference of a journal. So that's the acknowledgement from these people are doing. And this green chemistry is a journal started by this Royal Society of Chemistry who are sponsoring this thing. That's journal, the first attempt to bring the publications of green chemistry in one journal. That was by Royal Society. It started in 1999. And now it's one of the best journals for green chemistry. It's a high impact factor journal now. So that's whenever some green process is, then you can publish it in, scientists published in green chemistry. Okay. Okay. Yeah. Another reaction. Okay, I don't know whether they have already studied Grignard reaction. That's a Nobel Prize winning reaction, very important reaction. So Grignard reaction usually done in a solvent and a dry solvent. When we are student, we had really lots of problem in making Grignard reagent. But now, if you look at the innovation now, the solvent-free Grignard reaction, those days, it was like that's such impossible. Solvent-free Grignard, how that is possible? You can do with ball milling. You can do this. This is a halide, any halide with magnesium metal. You can make this. This is the Grignard reagent. That's the real problem to make the Grignard reagent. But now you can make it in easily without any solvent. And then normal reaction, Grignard reaction, you can get these products. You can get the things. But what I emphasize here, that using the ball milling, using this mechanochemistry, you can make the Grignard reagent solvent-free in a green way. Okay. That's again the sodium borohydride I already told you. That's again used some solvent. But here again without solvent. With sodium borohydride you can do the reduction using ball mill. That one I saw, the ball milling is now a regular affair in a lab to do, regular tool in a lab to do the reaction in a Grignard way. Okay. Okay, this reaction now is a Nobel Prize winning reaction, the click reaction this year is just this. Because this molecule, this 1,2,3 triazole is another very, very important molecule. If you look at the scenario of triazoles, they are used for so many things. If you have the carbohydrate tagged carbazole, you have some other tagged carbamol, these are all used for some medicines and some things. So very, very important thing, this 1,2,3 triazoles. Again, if you look at the literature, there are from thousands of methods of making, say, 1,2,3 triazoles. All of them are using some solvent, some heat and all the things. That's one of the way we did it in our lab, that again in one pot. We are not making, it's actually making the reaction of an azide and alkyne. any azide and alkyne. But you have to make the azide before. But we did it in one pot, all alkyl halide, sodium azide, and all in one pot because azides are not very good things. So we did not want to handle it. Just put everything. And then this is the catalyst we developed, copper aluminum, that can be recycled for 10 to 12 times. And then that 600 RPM means that the revolution per minute, and 60 minutes, 6 balls, you can get this molecule without, again, without any solvent, without using much electrical energy at more or less room temperature, 40 degrees or so. So you can make this molecule in a very simpler way. That's one of the simplest green way of making 1, 2, 3 triazole without using any organic solvent and higher temperatures or any other costly catalyst. Copper is, this catalyst is very, very cheap. Copper sulfate, very cheap thing, and aluminum, they are both are cheap. And they can be recycled. Okay. Okay, again that one. Pitchman condensation, again, I'm telling you, this reaction is a century-old reaction, making the coumarin. This is, coumarin. This is a benzene ring, and this thing is coumarin, the dihydropyridine. So coumarin is another very important compound, natural product. It's a natural product. This reaction is century-old reaction. We can get from phenol and beta-keto ester. You can get this. Look at the 1883. It was discovered in 1883 first. But the disadvantage is stoichiometric amount of sulfuric acid, 4 to 5 sulfuric acid, high temperature and low yield. That was the problem, original reaction. So then innovation came. They found that all these things are using tosyl, paratoluene sulfuric acid, methane sulfuric acid. They can make some methods is better than earlier one. But again, use of large amount of methane sulfuric acid, that produces a waste. Yes, limited substrate scope and produces large amount of waste. That's the one thing. The waste is a big problem globally. So try your reaction in a way that there is minimum waste production. Okay, that's another thing. So how can you do that? So we did it. Yeah, that was the recent thing done with my, I say that Russian collaboration. We did it. I have some recent collaboration with Russia. So we did it, this same thing. So the coumarin, we made it, methane sulfuric acid only 0.1 equivalent. 0.1 equivalent, again, ball milling, you can get this molecule. We made many molecules of that. That's of the coumarin. Okay, one thing I want to, tell you here, look at the reactions. And one thing that, if you, I don't know whether you can see it, there is some figure in the parenthesis, 84, and everywhere there's some parenthesis. So I want to draw your attention on that. What is this? These things are called Ecoscale indexes. I will explain. Okay. Whenever you are claiming that your method is green, or when you are developing a green method, now people don't believe that you are tell the green, how green it is. So how green means you have to consider several factors. Your safety factor, your how much waste you are producing, and then also cost factor, all these things. Because green means just you are doing one reaction is green, that's not thing. So now, I mean, every journal or everything, whenever you are talking about, you have to tell the quantity way, that how green it is. In that way, yeah. This is, there are several parameters. Yeah, so I'm giving two important parameters, which is now usually sought, or where you have to give it, that Ecoscale. The Ecoscale indicates the simplicity and general applicability of a process. That's very important. Your process should be simple, whether that can be used anywhere. That is the useful. Okay? And general applicability. It can be used in general, all the things. The parameter considers cost. That's important. Cost, safety, technical setup, energy, and purification process. All this is very important for industrial application. So the higher the value, the greener is the process. And this in our procedure, the Ecoscale is more than 80% in most of the synthesis. That is important, that how green it is. It should involve the cost, how much your cost, how much the safety. That's very, very important. So these things are very important. That's why I'm telling that whenever you are telling green, you have to tell how much green it is. Others people will not believe it. Okay. Another thing, E factor. E factor, that the total waste, is a quantitative tool to evaluate the quality of an organic process based on the generated waste. So the lower the value, the greener the process. So this waste is, I told you from the very beginning, I'm telling that waste is a global problem. So you have to minimize and eliminate the waste. And all the reactions I'm showing that there is no waste. So in this reaction also, if it is less than 1 or as minimum as possible, the waste is less. In our process, the wastage E factor is 0.67. That's considerably good E factor, that it makes less waste. Okay, these two things I'd like to introduce you. That's very good. Okay. Okay, and next, okay, so here I'm just the highlights. This is ambient reaction temperature, low catalyst loading, all the things, solvent-free reaction, improved selectivity, it's a low E factor and high Ecoscale. That's the important. Okay. Now I will, that is so if you look at again the photosynthesis, they use what sunlight. So whether it is possible to do the reaction in sunlight in real life? Yes, it is possible. Again, in the deliberation also, there are many reactions during sunlight or visible light. I will show 1 or 2 examples, 3 examples maybe for using sunlight. This reaction I demonstrated in the colleges or schools many times, that what you can do, that's a real green photochemical reaction, that is photoreduction of benzophenone to benzphenacol. You know, this is benzophenone, that's a ketone, benzophenone. You take in a Erlenmeyer flask or conical flask, you take benzophenone and then put in some isopropanol and in presence of acetic acid. Just then put it in any sun, roof or anywhere and forget it. After 4 or 5 after 4 or 5 hours, when you bring back the flask, you will find fine crystal of benzphenacol. When you put the flask, it's all solution, homogeneous solution. But you put in the sunlight, direct sunlight, very good sunlight, then within 3-4 hours, you will get really good crystals of benzphenacol. So that's one of the very important, I say the nice example of demonstrating the effect of sunlight for doing the reaction. There are many, but I'm just one example which can be demonstrable. I'm asking the teachers, you can show your students that this reaction, that's a very important reaction. You can show to the students that how sunlight can induce reaction. That's a very good example of that. Okay. Now, again, sunlight is okay in the outside, but when you do any reaction, can you do it always outside? You cannot. So you have to do it in the lab. So what can be the equivalent of sunlight? That can be normal diffuse light, or now people are using LED light or CFL bulb. All these things can be equivalent to sunlight, and they are also doing many reactions. Okay, in the last 3 days here also, many scientists show that's the visible light reactions and many important reactions. Okay. One of the examples here again, they're using blue LED. As I told you, the equivalent of sunlight is blue LED. Here, they're making photoannihilation of pyridine. This is pyridine, okay? And then the photoannihilation, if this, again, I'm telling diazonium fluoride, they're making a good things for making radicals. So these are not fully environment friendly, but it's less toxic. With blue LED, again, water, oxygen, that's normal oxygen, room temperature, nothing, no solvent, nothing else. You can get this photoannihilation of pyridine or substituted pyridines. There are many examples of that. So you can make this reaction in real life. Okay. Okay. Another reaction, that is coupling reaction of 1,4-dihydropyridine, similar reaction. If you have a diazo group with blue LED and argon, you can get radical here. You can get radical here, and you can make this compound. The dimerization of pyridine, dihydropyridine, you can get this compound. These compounds are very, very important compounds. Okay, I'm skipping it. Again, another way from my lab, that is the percentage of biheteroanyl. Biheteroanyl, very important compound. Here also you can get this aniline, and then any heterocyclic molecule with tertiary butyl nitrite, eosin-Y, DMSO, and all the things. You can get this. This is again transition metal free, additive free, acid free, room temperature. You can get these things. Okay, I think I am almost. Okay, now So what I want to say all these things, that what is the take home message? I'm just demonstrating all the things. This is the take home message for you, and remember it for the budding chemist, that whenever you will really practice chemistry in the lab, keep in mind that if chemistry is practiced in the nature's way, certainly you can make this world a better living place with clean environment. That's the message, that when you start your chemistry life, your research life, keep in mind that whatever you do, try to do in a way so that we will not harm the environment, we will not harm this world, so we can make a better living place with this. And now the trend is that, as I told you here also last 3 days, the trend is that now the chemists, they are working on that, and one day possibly we will make this world a better world. So maybe very soon we will be able to tell that chemistry for wellness, not for harm. As I told you that your neighbor is telling chemistry is bad, but maybe very soon we will be able to tell them, no, chemistry is not for harm, it's for wellness. Chemistry to save lives, not to kill. Okay? And chemistry for comfort, not for discomfort. So if we really practice chemistry in nature's way, then at one day, or I believe it very soon, we'll be able to tell all these things, that chemistry is for wellness. Chemistry is not for any other harm. So we can say that be proud to be a chemist. Say, joy ho chemistry. Okay, thank you. Okay, last 2 slides that, yeah, I quoted my works where I just really express my acknowledgement to my students whose names are there. Okay. And this, for support my institute, where I'm starting my beginning of my career, I'm there, Indian Association for the Cultivation of Science. And recently, Ural Federal University in Russia. So went for fund, always DST, and now INSA. And now I thank you all. Okay.
So now the forum is open for questions. Students, teachers, participants, all of you are encouraged to ask questions. This is a brilliant opportunity because he is a pioneer teacher, a great teacher. So please feel free, overcome your nervousness and come up with any questions you heard.
No, why nervous? Don't.
You already probably got the insight, and we can probably say that chemistry is the mother of all science. Starting from toothpaste, toothbrush, to the medicine we take everywhere, chemistry is related. We saw so many molecules today. So, questions from students? Anything, yes. Any thoughts you have? Please feel free. Yes, please. Yes.
Okay, I'm
introduce yourself first.
Okay, I'm more close to you. Okay. Feel free. Yeah, sure.
So this is Agniti from Kendra Vidyalaya number 2. Currently I'm studying in class 11th. So recently at the National Children's Science Congress, I did a study over the topic that what are the harmful effects of the crackers. So as you told us about the philosophy of green chemistry, can we apply this on crackers? Like many harmful products, chemicals are used in crackers. Can we make some crackers without using such chemicals by using the philosophy of green chemistry?
Sure. I think. Yes. Already have heard the green crackers. Now the High Court and Supreme Court has ruled that you have to use the green crackers. Okay, you have heard these things. So these crackers are relatively, I'm saying not 100% safe, but relatively safe. And you can use some chemicals, I think this, or some salts, which are not that harmful. It's possible. It's possible, and see this thing is now improving. It's okay. So it's not that in one day you can convert everything green, but you can. And the initiatives are going on, efforts are going on. I think now the scientists are motivated, and you people are more motivated. So with my talk, if you are getting more motivated, the Future depends on you. Okay, sure. You will make really 100% green. I believe it.
So
Anyone?
who is coming up next?
Anyone say, please? If you have any queries, any questions, feel free. No problem.
Yes, even teachers are welcome.
Yeah,
Please
sure,
feel
sure,
free.
sure,
Any
sure.
tips on teaching?
Oh, sure.
Any suggestion you need? Sir is there. Please feel free.
And teachers, I'm just suggesting you that if possible, whenever teaching, give some lessons about the green chemistry. Tell them what is green chemistry. Tell them that how to practice chemistry in a way. Or whichever is bad, tell them this chemical is not good. Or at least tell them that this chemical we are using, but it's not good. They should know it.
So right now score is KV1.
Come on. Yes, who is the next one? Some boys, please. The girl already did her job. Come on.
Anything, you can ask anything. Whatever is not talked here, you can also feel
Yes,
free.
please.
No problem.
Hello.
Yes.
So, hello everyone. My name is Prince and I'm from grade 12, SP Global School. So, sir, my question particularly is related to academics. We all know that some students fear chemistry. They don't actually like chemistry because there are so many reactions that we have to learn. So, sir, can you enlighten us that how we should actually study chemistry in proper way so that it could benefit ourselves in life and also in academics?
Yeah, that's what I talked about. That's okay. That chemistry, okay, another I'm telling you, the green chemistry, if you read it in the books, there are big definition of green chemistry, the 12 principles of green chemistry, all the things you have to memorize. What I told today, that you didn't memorize the definition of green chemistry. You did not memorize the 12 principles of green chemistry. Just you remember the photosynthesis. That's very simple. If you remember photosynthesis, you can derive all the principles of green chemistry. You can tell what is green chemistry. Okay, I'm telling you. Have you followed that photosynthesis?
Yes, sir.
Okay. Now if I tell you what is green chemistry, can you tell me? That just from photosynthesis?
So maybe using all green tool, you specifically mentioned the
okay.
green tools.
Okay, so that's nice that you have not studied the principles of green chemistry, you have not studied the things. So that's one of the way, I'm just demonstrating the way to teach chemistry. So the teachers should teach chemistry in like a storytelling. It's not like that big things or the big definitions, the big mathematics. So if the chemistry is taught in like story like that, it will be attractive. That will be the things for chemistry, I think. So it should not be say make your memory very jam. It's not. It should be like that, but simple thing which you can understand, and that is possible. That is possible. Okay. All the teachers I'm asking that way. Okay. Don't tell always whatever in the book. Try to tell them whatever like a story. Okay.
Yes, please.
Yes, okay. Yes, okay, no, mic is not working.
Morning, everyone. Good morning, Professor Sir. My name is Akshat Kapoor. I am from Montfort School, UK, where I study class 12. So recently we've done a titration experiment in our lab. To detect the level of oxalic acid in guava samples.
Okay.
So in one of the slides we have shown about the pressure and water. We have used it in our experiment. But during intermediate steps, we have used sulfuric acid, dilute HCl, to get desired result. To detect the oxalic acid level in the guava sample. What can be the other way to reduce the use of these acids so that we can get the desired
Yes, nice question. Yeah. You may avoid the use of this mineral acid like sulfuric acid or HCl by using some other things like sodium bisulfate. I don't know. So you can use it. Many reactions can be sodium bisulfate, or you can say some sodium chloride or some other things, some acid or which are less harmful. You can avoid sulfuric acid. There are many ways. of doing the, or paratoluene sulfonic acids. I don't know exactly what this is, but that is possible. In theory, that is possible to avoid the sulfuric acid by many, many things, many alternatives to sulfuric acid. Yeah.
Because
Sometimes clage, yeah. What?
With the experiment, we have error titration. We have so many for the waste product. This byproduct is formed. It's very harmful because it's
yeah. That.
And I have a headache for 2
days. Yeah. That should be. I think. Yeah.
Cases traced to that experiment.
Yeah. Yeah. I believe that that can be alternative thing, and I asking the teachers to find out that's alternative to sulfuric acid and to make these things. That is possible. That is, yeah. If I look at the chemistry, I can also make it, but I think your teachers can do it also. That's not impossible.
So next, yes, sure.
Good morning to everyone. Myself Sharia Manan from St. Anne Senior Secondary School. So my question is that plastic is a very big issue now. So can we make some bioplastic so that it is degradable?
Sure. Yeah, that's already done. Okay, because I cannot tell everything in my one lectures. I can give one lecture on bioplastics. Okay, basically what is plastic? That's a polymeric material. Simple thing is that if you have ethylene, if it polymerize, you can get polythene. Okay. So that's the thing. Now, what is bioplastic? These plastics are not biodegradable. Now, if you can make polythene from natural product, again I'm telling natural chemistry, nature's process. I'm telling you one example that is done by Laddock long back. I mean, that time, in 2002, I think, 2002 or 2003, I visited the Iowa State University where Laddock worked. He showed me, that time, the beginning of these bioplastics, he showed me that from the corn oil has unsaturation. You need a double bond, that's all. You have to polymerize an olefin. So you need a double bond. So corn oil has double bond unsaturation. So he made plastic from the corn oil. Okay, he showed me that in the lab, that this is the estimated. And after that corn oil, I mean, it is not commercially that, viable because the cost is high. But later, the bioplastics now made almost, all the developed countries, that they made the polymer from a biodegradable substance, particularly the nature's olefinic product. And these bioplastics are degradable and are being used, in many countries. Yeah, that's possible.
It is not being used in India till now.
It's cost because of the cost.
How can it be feasible in India?
No, it will be possible if you can make more, or technology is say more advanced. So you can, I think in one day it will be naturally available in India too. Plastics. Available. Yeah. India. So it's available in India. Yeah.
Thank you, sir.
But technology is known now. It's a well-known technology. Yeah. Even, okay, I'm showing you what. In one of the experiments, I saw it in college, that's from the peel of potato. We made in the lab, we demonstrated, we made the peel of potato, we can make the plastic. That was in book. You can find it in the Google also, you can find it. The potato peel, that is, you can make it. We showed it in the lab.
Thank you, sir.
Yeah. So someone else? Yes, please.
Sure.
Mike.
Good morning, sir. I'm Pranjal from grade 12 from Mount Liturgy School, Urki. Sir, I wanted to know basically that we are here today to know about some contemporary facets in organic synthesis. So, sir, I wanted to know what is the basic meaning of our topic presented here. Like we have studied many things that we don't know even now, but some reactions we were aware of, like reduction and all. So, I wanted to know basically what is the meaning of contemporary facets in organic synthesis. I have searched it yesterday, but I didn't get anything.
Okay. Science is ever changing, always. Chemistry is also changing. Everything is changing. Say, organic synthesis, when it started 100 years back or 150 years back, it was the time this. Now it's changing. So contemporary facets means what is going on in today's lab. As I told you, that green things and all the things in the lab, in the last 3 days, many people, I'm a scientist here, are changing how catalyst can be designed, how reaction can be designed in a new way, a cost-effective way, greener way. That is the contemporary facets, means the recent phase of organic synthesis. Recent phase of organic synthesis. That's what is talked about for last 4 days. Okay, yes. Then summarize it is what is that recent phase.
Yes, sir. Another thing, sir, in between of the presentation, I have heard about topic mechanochemistry, and you
Yes.
told that we'll study about it later. Sir, I wanted to an overview of that mechanochemistry so that we can also explore some more about it.
Yes, okay. Yeah, very, very nice, and if you're interested, that's good. Mechanochemistry is the chemistry generated by application of mechanical energy. Okay, and that's a new field, relatively new field, but although it's relatively new means earlier it was. Then there are many books, and one of the book I have written, that is the first book of mechanochemistry in 2015, published by Royal Society of Chemistry. So if you Google, if you go to Amazon, you can find that thing. If you put my name, you will find the book there. That's first. That is the ball milling reactions. Green, I think, green aspects and challenges.
Yes.
So that's marketed by Royal Society of Chemistry, and you can get it in Amazon.
Yes.
Okay, but
Thanks.
there are many other books. I'm not. There's the only book, but that is the first book. That's which I have written. Yeah.
Thank you, sir.
So,
Yes, please. Pass on.
Good morning, everyone. Good morning, sir. So you have told, my name is Radha Pandey from Kendriya Vidyalaya number 2 Roorkee. So you have told us blue LED gives energy to the reaction given by the sunlight. So sir, my question is how the blue LED is producing the sufficient energy for that reactions?
yes. Okay. When your sunlight is wavelength matches with the blue LED. Okay. So the blue LED is an alternative to sunlight. So, okay, when you are applying some light or sunlight, what you are doing, you are affecting on the molecule. It's a vibration or some excited state or some changes is done, and in that way, it's somewhere it becomes excited. Okay, when the molecule reacts, that means it must be excited. It's not in the ground state; they don't react. So by applying the light, you are exciting a molecule to react with some other molecule. Okay. That was the purpose of using light or any energy. Somehow, for doing any reaction, you have to excite your reactants. Right? Like you two were that sitting together. You don't quarrel. But someone excites you, someone provoked you, that person is abusing you or something, then you turn into quarrel. So like the same reaction, that you have to excite one molecule or two molecules to get the reaction done. So the purpose of using light or sonication or mechanical to excite it some way. Okay?
Thank you, sir.
Understand? Yes, okay. Yes.
Yeah.
Sure. Yes. It's not working.
This is Vandana Soni from DPS Roorkee. So I want to ask one of the experiment we used to do in lab, and the students also perform that is salt analysis. So will it be possible with all of the vegetables or green substances to analyze all those ions that we used to do?
Sure. Why not? You can. Sure, you can.
So from all of the green substances, we are not getting much of those ions. Then how can we do that?
No, you have to pick up the particular vegetable or particular things which contains that metal or that things. Yeah.
Yes, just say,
you have to look at the literature. Yes.
Suppose for oxalate ion, we can take a guava.
Yeah, I think you can get it also some other vegetable like yam or so that have also oxalic acid.
Okay, yeah. Okay.
There are many. You can look at the literature. You can find it.
Okay.
Yeah. Sure.
So I think we will have more questions, but you can grab during the tea session and other things, because we have other programs to follow on. But as we know, you are the world, you are the children. So future generation, keep motivated, keep doing well. Imagination is the source of creation, right? And just to add a little note, sir is from the institute, Indian Association for the Cultivation of Science, which has brought the only Nobel Prize in Science to India till date. Sir C.V. Raman worked in the very same institute. So with this, keep your spirit high, and we end this interaction session and move on to our next session. Thank you all for your extreme participation, and student spirit has made the program extremely delighted. Thank you so much.
I'd like to add siege also.